Okay, there we go. Hi, everyone. Welcome back to the Toronto Data Workshop. This week we have Laura Plein, currently at University of Luxembourg. She's going to talk about whether LLMs can demystify bug reports and translate them into test cases. So she conducted this research while she was an intern at the TRUX, which is the Trustworthy Software Engineering team at the University of Luxembourg. But she is actually going to be an incoming PhD student starting in September once she finalizes all of that. Her current affiliation is with Saarland University. So thank you very much for joining us, Laura. I'm very much interested in your talk.
Well, thank you very much for inviting me. So I'm very happy to discuss my previous research with all of you. So as you mentioned, today we'll be discussing a little bit on how large language models can be used to kind of understand bug reports and translate them into test cases. So I think we've already used a lot of software, and one of the common issues are that we always find some bugs. The problem is usually, people report them in natural language, and then the project owners just get a whole lot of bug reports. So currently we are mostly lacking some tools to automatically address those bug reports, because of course software is tested before it's actually being deployed. But of course, those test cases are usually not really covering all the functionality. There's always some user trying out some complex execution where we discover new bugs. So of course, people report them, and then we have them in natural language. So right now, if we have a bug, of course, if we want to address and fix it, the first step is to actually reproduce the bug. So already here, software maintainers already struggle because, of course, they don't know exactly what the bug is, or they might manually try to reproduce it, which is very time-consuming. And of course, even once you reproduced it, it's still a long way to actually really localize and fix the bug. So previously, there have been many tools already to automatically repair software. The problem is that they all need a test case to actually show that there is a bug, and then this can be used afterwards to localize and fix the bug. So here we are clearly missing those bug triggering test cases, since clearly they were not in the initial test suite, otherwise we wouldn't have the bug anymore. So here, what we clearly need is to have new test cases to enhance the previous test suite to reproduce the bug. Here, another issue is that we don't necessarily know how the software actually should behave. So usually when a user reports the bug, he describes that in natural language in the bug report. So usually there we have some information on how the software should actually behave. But now we still have the problem that we cannot directly use this. So we need to find a new way to automatically generate test cases that will actually now detect this bug. So there have been many tools that can be used for automatic test case generation, such as, for example, EvoSuite, which is really great if you have like a big Java project, can generate you test cases for all kinds of classes. But if you have a bug in your software, you don't necessarily want to generate hundreds of test cases for all the classes in your software. So you want it to be specific for the actual bug. So here, one other issue is, so here we really need like some formal input. So the exact class, for example, that is buggy, which we don't have. So for us, we cannot really use those tools because we only have some informal written bug report. So therefore, here, what we actually want to figure out is we want a way to automatically generate test cases. So this will actually be able to solve many problems, and this can be also useful to localize the faults and afterwards to validate patches. So here we have just one example of a typical automated program repair pipeline, which is one of the tools also developed by my team. So for example, we have some template-based program repair approaches where you just apply different fix patterns until you manage to fix the bug. But here, in order to determine whether the bug is fixed or not, we need, again, a test case that differentiates between the buggy and the fixed version. So here, again, we cannot apply any of those tools since we're still lacking the test case. So here, basically being able to generate test cases that address the bug, it will not just help the developer to find and reproduce the bug, but then we can actually leverage many tools that have already been implemented, because there are many great automated program repair tools, but they cannot actually be applied in practice just because we're missing the test case for the bug. So this is what we're aiming to solve in this research. So the general idea was, as we saw before, there is a huge amount of bug reports. So here's just one example. So this is one example of one bug report where we can see that the user is really explaining what the bug is with some specific inputs as well. So here is, for example, the original test case that was manually written by their developers. So now the question is, how could we now actually generate this test case, for example? If you would just get this bug report, assuming it's a new bug that is reported. So now the question is, how can we now automatically generate this, since this is clearly what we need in order to address the bug? So here come in, of course, large language models. So here, this was just a very quick overview. So we have seen much progress. So this work was mostly done beginning of 23. So now I know there are much more popular and more powerful tools that have arisen as well. But already there we have seen also with ChatGPT, many software tasks, like trying to use it to overcome some challenges. So large language models have already been known for a few years to be good as well in code to natural language tasks, as well as also natural language to code tasks, which is actually the problem that we are facing here. So therefore, the main research question then was, is it actually feasible to use such a large language model to then translate those informal bug reports into bug triggering test cases? So our study was actually, so in this case, the general overview was that at the end, we wanted to be able to just take the bug report, feed it through our model, and get a test case. Of course, for the test cases, we had to first check if it's actually executable, which unfortunately is not always the case. And afterwards, checking whether it's then actually failing on the buggy project. And if yes, we can then use it to actually address the bug. So for this study, we actually work with a database called Defects4J. So this is a database with real software faults for Java projects. So this is one of the commonly used benchmark to evaluate all kinds of automated program repair tools. So here we reconstructed pairs of bug reports and failing test cases. This was one of the few benchmarks where we did not just had the buggy and fixed version, but also the bug reports that we really wanted to work with. And for the models, we have been on one hand using ChatGPT, and on the other hand, we were also fine-tuning CodeGPT. As I mentioned previously, now again, we could extend this study by fine-tuning much more powerful models, and I'm sure we would get even better results than we had previously. So for the evaluation, we distinguished in a few metrics, actually. So the first and very important one was simply that the test case needed to be executable. But just because we had an executable test case doesn't yet mean that it's actually useful to address the bug. So in a second step, we were actually defining the word validity. So if we talk about a valid test case, we mean a test case that is actually failing on the buggy project, which of course has to be essential to detect the bug. But even if it's failing, doesn't necessarily still means that it's really the perfect test case, because of course, if it's really relevant for this bug, it should also afterwards pass on the fixed version. So then if it's failing on the buggy version and passing on the fixed version, then we actually called the test case relevant to the bug that we wanted to address. So in the general study, we wanted to see if it's feasible to translate the bug reports into test cases. So we first constructed some baseline experiments with just using ChatGPT to see if in general a large language model can be used for this task. And then we also evaluated how the results are compared to actually fine-tuning a model on the task, because we thought it could both be interesting. And of course, we also need to make sure how it works on new bugs, because as we all know, ChatGPT has been trained on a huge amount of publicly available data. So we had to make sure that it's also working for newly reported bugs. And for the rest, we were also wondering, how does the bug report quality actually influence this generation? Because of course, there are some users that just write like in one sentence, there's a bug, something is not working, which of course is not very helpful for test case generation. And some other users really described like with some function names and concrete inputs of what the problem were. So there we also wanted to see like how much the impact of the bug report quality is on test case generation. And on the last step, we will just have a look on how our test cases can actually be really helpful at the end to run a whole program repair pipeline. So as we've seen, we also ideally want to address and fix the bug and not just reproduce it. So for our first experiment, here we have again the bug report that I took as an example before. And if we feed it to, for example, ChatGPT, we can here already see an interesting generated test case where we already find clearly some commonalities with the bug reports. So it's really recreating using the parser that the user described in the bug report, and it's also really using the inputs from the bug report. And of course, one thing we also had to check is that it's not exactly the same as your original test case, because otherwise we could think, okay, it just remembered the exact developer written test case that it might have seen during its training process. So here we can still see that it's different from the original test case. So in general, for ChatGPT, as we all know, if we ask the same question 5 times, for example, to ChatGPT, we might end up getting very different answers. So on one hand, we did some first experiments by asking ChatGPT only once to generate a test case. And there we only got an overall executability of 15%, which was quite low. But if we did multiple iterations and asked ChatGPT, for example, 5 times to generate test case, we already got an executability score of 50%, which was already quite interesting since they are quite complex software project. So they were already happy to have 50% of executability. And also already for validity, we had 30% of valid test cases, meaning that 30% of the test cases were indeed failing on the buggy project. And here we had 9% that were also passing on the correct, on the fixed version. So in general, having a few more generation can be helpful. But we were already happy to get already some test cases generated that were really helpful by simply just querying an LLM. So in the second step, we wanted to see a little bit how fine-tuning affects those results. So here we divided the defects for J dataset in training, testing, and validation. And here, one thing that was interesting, so if we compare the single generation, there we had, for a single generation, we clearly had that our fine-tuned model was better performing than ChatGPT. However, if we performed multiple generation, then the executability was actually higher with our ChatGPT. So here with ChatGPT, we had like a much bigger variation between 1 and 5 generation, which is actually normal because their ChatGPT has seen much more data and is used to give more diverse input. However, when we fine-tune a model, we are expecting it, since it has only seen this limited amount of data, to usually like quite repeatedly the generation were very similar. So either it was able to generate it or it was not. So the only difference there was that with our fine-tuned model, we had some issues that sometimes the test case was just not generated until the end of the test case. So then if we did it a few times, then sometimes we were luckier and the test case got actually generated until the end. So that was one of the main differences here. But in general, we were also quite happy to have already some results here. And as mentioned previously, I'm pretty sure that if now we would, again, fine-tune more recent and more powerful models, we could significantly improve those results. So in this whole study, we wanted to demonstrate our first feasibility of really using those bug reports in natural language to actually address the bugs. So this was more like first study that we also plan on further improve on. So here we have an increased executability for single generation, but not for multiple generations. So now we need to see what happens if actually a new bug gets reported. So here we took one example from the Lang project. So here we have actually a quite short description, but even though the description was quite short, we got a long test case that was generated and it was executable. So in this example, it was not failing, but we got an executable test case for a newly reported bug. So in total for the project in our study, we were quite limited in what new bugs were reported. But for those that we could find, we overall had 47% that could be translated into executable test cases. So already this also showed that the general idea of using bug reports to generate test cases can also work on newly reported bugs. So we were quite happy because we were worried that it would only work for bug reports that the model has previously seen. So now when it comes to the impact of the bug reports, so a first study was simply on the size of the bug reports. So in general, we can already see that the more details there are in the bug report, then the easier it is to generate a corresponding test case. So, but actually whether the test case is executable or not doesn't seem to really be dependent on the size of the bug report. However, we have seen that the actual relevant test cases, there in general, the bug reports were quite larger than for the other ones, which was quite interesting because personally I was expecting to see a larger difference between executable and non-executable test cases, but here there didn't seem to be a significant impact from the bug report size on the actual test case. So usually for this study, the bug report size only impacted the relevance of the test case. Another study that we did was to actually analyze the code presence in bug reports. So some users just mentioned, for example, the function name, others actually added one or a few lines of code into the bug report. So here it's just important to understand how we defined code presence because there were really many different variations. So if a user only mentioned a function name, we considered it as no code, as it was not possible to actually simply run this code and have something executable. So as soon as there was at least one functioning line of code included in the bug report, we consider it as code presence. So of course, there were many different variations. So here was just one example. So here we can see that for the non-executables, there were only 60% of the bug reports that contained some code. And already if we have a look at all the bug reports that led to executable test cases, we can already see that the proportion of code in the bug reports was already slightly bigger than for the not executable ones. And here again, we have the biggest difference for the relevant test cases. So in order to really have a relevant test case for the bug, it's definitely beneficial to have some kind of code presence. Even though the code presence might be as little as just one line of code, this can already be really helpful for the model to really generate an executable and relevant test case for the given bug report. So here we found the code presence to be very important for the generation of relevant test cases. So also good for us to know in the future, if we write some bug reports, that it will be helpful to add even just a little bit of code. This can really speed up the process of fixing the bug. So now we have already seen that we can generate test cases, and we have seen the importance of the bug reports. But now, of course, we want to see how important those test cases actually now are in order to also localize and fix the bug. So here again, we have a look at the general automated program repair pipeline, where most techniques start by localizing the faults using the test cases, and at the end, validating the generated patch again with the test suite. So for the fault localization, many techniques actually use spectrum-based fault localization, where you look at the execution traces during the execution of the test cases. And there is a tool called GSoltar, which is usually used in order to get a ranking of suspicious source code lines. So here we performed several variations of the fault localization, and we will come to the results in a moment. And for patch validation, it's important to distinguish between plausible and correct patches. So a plausible patch is a patch that managed to pass the test suite. But there, unfortunately, usually if you have one buggy function, you can just remove the buggy function or all the code in the function. Then, of course, we will pass the test suite. So this would be a plausible patch, but of course, that's not an actual correct patch of the software. So here we have to make sure that the patch is actually semantically equivalent to what the developer would have written as patch. So those two notions will also be important for the next question. So if here's just one example of one of the bugs where we can see that there was just one buggy line in the code. So here we see at the top, we see the file that was buggy and the exact line. So if we want to perform spectrum-based fault localization, the results would look something like this. So here we get the suspiciousness score, and we have then those in a ranked list. So here we can see that the suspicious line here was ranked as 7th most suspicious line. So here, this was when we performed the spectrum-based fault localization on the original test suite. So it was in top 10 lines, but it was not the most suspicious line. So it would not be the first line that we would try to fix if we would use some repair techniques. So in order to see how our test cases would perform, we did not just added them, but we first removed the test cases that were originally triggering the bug, and we replaced it with our generated test case to really see if our test case was able to localize the bug. And here was now one example. So here with the generated test case that we generated, we could now see that it was the first reported line. So how well does it work in general? So on one hand, we distinguish between where it's written GZ1, it's whether it was the top one most suspicious line, but we also investigated if we were able to detect it in a top 5 suspicious line, because this is already quite good and helpful if we can at least have it in the top 5 suspicious lines. So we first run the whole experiment on the original test suite, and then a second time where we removed the bug triggering test case and replaced them with our generated test cases. So here we could already see that we were able to slightly improve the spectrum-based fault localization with our generated test cases. So they really can enhance the detection of the buggy line. So also we could, of course, also just add them and use them in combination with the previous test suite, or we could even in the future generate even more test cases to even further improve the fault localization. But we were happy here to see that we could improve for some project the top 1 buggy fault localization and also the top 5 fault localization. So here it seems that the generated test cases can really be helpful to actually then start the automated program repair pipeline by actually enabling to localize the fault. So the last part was on the patch validation. So here we used again the patches that were generated by T-bar, and here we always distinguish between the actual correct test cases and the plausible, the correct patches and the plausible patches. But of course, even though those tools are really improving, they are still not capable of generating patches for all the bugs. So for example, for the closure project, even though there are over 100 bugs that were in the project, currently state-of-the-art tools were only able to generate 17 correct patches and 9 plausible ones. And for this project, we were able to generate 35 valid test cases, or 35 test cases that were actually failing. But if we took the intersection, we were only able to find 6 bugs for which we actually had as well a plausible patch as well as a valid test case. So therefore here, if we take the intersection, we are still quite limited because on one hand of our approach, so we were just able to generate a certain percentage of valid test cases, but also the program repair tools are currently not able to fix all of them. So here we were already happy to see that for some of the projects, we were able to actually validate the patches. So from this intersection, we were able, for the lung project, we were able to correctly validate 2 correct patches, and we were able to validate 2 of their plausible patches. However, not validating plausible patches is not necessarily a bad thing. So as we have seen before, a plausible patch might simply just remove functionality. So for those, it is actually helpful if our test case is not validating those patches, because maybe our test case is checking more functionality, which is missing with the plausible patch. So then it can be helpful to discard those patches and to further continue generating new patches that actually pass the previous and our test cases in order to really have a higher amount of correct test cases. So it can be used on one hand to validate correct patches, but on the other hand also then to discard incorrect plausible patches. So in general, then we have also seen that the test cases generated just from their bug reports can really be used for the whole automated program repair pipeline. Of course, our approach comes also with some limitations. So on one hand, for our dataset, our experiments were only performed on Java source code. So there could be very interesting to also perform this, for example, on Python code, which is also used quite a lot in practice. That would also be very helpful to address those. And also for fine-tuning the data set was quite small, but it was quite hard to find interesting data sets where we really had the buggy fixed version and the bug reports, even though there are many bug reports reported, but they are not necessarily associated with a clear buggy and fixed version and a test case. Also for the model, since this work was performed now a little bit more than a year ago, now it would be very interesting to see how more recent, more powerful models would perform, since they're really, we have an exponential increase in capabilities of the models. So there, for future work, this would also be very interesting. Another thing is that while manually looking at the test cases that were, for example, not executable, in most of the cases, it was just that there were important imports, for example, missing. So our models only generated the test case itself, but not the relevant imports. So here we could also see in the future how we could automatically improve this to just make sure that all the important imports are there. Then we would already have a much higher amount of executable and potentially relevant test cases. Another idea is we have already seen some work done on so-called conversational APRs, so to iteratively try to fix the program. So we could actually use similar techniques. If we see, okay, the test case is not executable, how can we then continue the process until we really have an executable test case and then see whether it actually reproduces the bug. So there's still a lot of work that we can do, and also some of my colleagues are still working on similar, very interesting topics. So I'm not going to reveal all of this for the moment, but we're still working on improving this as well. So for now, what we could conclude is that we were able to actually generate executable and also some relevant test cases with the two models that we tested. We have also seen that it is indeed possible to use the bug reports of new bugs so that we could actually then really address them and help software maintainers to automatically fix the bugs. And we also have seen that the bug report actually does influence the test case generation. So make sure to write good and precise bug reports in the future. So in general, also for those that are interested, so what I presented today was mostly on those two papers. So a first version where we just checked the general idea of demystifying bug reports, and then the full paper covering everything that I've presented today. And we have also some interesting similar topics where we investigated how we could actually use the inputs, extract inputs from bug reports, and then still use other tools such as, for example, EvoSuite to generate test cases. So that if you're interested in that domain, feel free to check out what our team did or contact me. So we have some more interesting works in that direction. So here I also want to thank my team, which I have done all this work with. So I was very happy for the collaboration that I also still have with them. So with that, thank you very much for your attention. And if you have any question, I will be happy to discuss with you.
Thank you very much, Laura. I'll stop recording.